get this far in the notebook. When you look at the notebook from Friday, you'll see that the second part is that I bring into it sex of the penguins. And two things are important about this part of the notebook. One is that it gives us a categorical variable. And this notebook introduces how to transform using the one-hot transformer, right? When you do any kind of categorical x value, you're going to want to one-hot it. The other thing that's important about this is just the idea that you can do this in a seaborn pair plot, and you can use this technique as a good generic data exploration technique, right? So if you have things like males and females, this bit of code is how you can take the hue order and use this pairs of hues things in seaborn color palettes and have males and females on the same species be different darknesses of the same color, okay? So this is a good generic technique. But what I wanted to point out really from machine learning standpoint is that we have two transformers here. The one-hot for categorical variables and the scalar. The scalar variable, we've talked about this one in the past too. Z-score a column. Take a column, take it from, maybe it ranges between 0 and 1 million, and turn that 0 to 1 million into how many standard deviations away from the mean of the column is each data point. Okay? And that kind of thing is generically for anything that's mostly close to normal, or at least close to a centered, non-skewed distribution, you're going to end up with variables that are somewhere like, -4 to +4, pretty much. Can't really get much more than that, especially if it's really normal. So that way, columns have roughly the same order of magnitude if they're numeric when they're z-scored, right? You got one variable that's between 0 and 5. You got another variable that's between 1 million and 12 million. And after z-scoring, they're both roughly between -4 and +4. And now those two variable types that are radically different magnitudes in their raw metrics, they're on the same scale. And we know how that can help out anything that's linear algebra-like, because now the weight values also are on the same order of magnitude. And the weight values are comparable between different variables. Okay, so again, there's a bunch of BS in here that you should look over on your own about how to one-hot transform, how to do a bunch of pandas-style manipulations to replace raw values with one-hot values, or numeric values with the standardized values. Okay? The details are not important. You should just learn them. But what I do want to point out to you, decision trees. And I think I said this on Friday, but I've forgotten, so I'm just going to say it again. Decision trees, how do they make their decisions? Is it across variables or just one variable at a time? One variable at a time. Okay? Because decision trees make their decisions one variable at a time, it does not matter if feature 5 is order magnitude 1 million and feature 12 is order magnitude 1. Because each decision is made independently, the threshold is independent, we don't have to use a standard scalar for any quantitative variable in a decision tree. Now, that is not generically true. Other kinds of algorithms, like a nearest neighbor algorithm, don't make their decisions one feature at a time. What does nearest neighbors do? Could somebody say it in 2 sentences? Yeah.
It finds an odd number amount of nearest neighbors and sees the categories of them and sees which one's the max.
Okay. And how do we find nearest neighbor itself?
Measure the distance.
Yeah. So a vector distance, right? And a vector distance it's all the features at once, right? It doesn't matter if it's x1 or x2 or a combination of x1 and x2 on the diagonal, right? So all features matter at once. All features are part of the vector distance of what is a nearest neighbor. So there is a mixing of information in between different features. And if feature 1 is order magnitude 1 million, and feature 2 is order magnitude 1, well, now we have a problem, right? Now for our nearest neighbors, we'd better use a standard scalar for any features that are different orders of magnitude. Otherwise, we're going to get wrong answers. So that was me queuing you up about what the rest of this notebook looks like. Okay? When you go through this notebook, you will see that I make you at the end do nearest neighbors with and without a scalar. And when you do it with and without a scalar, well, you're going to get different accuracies. You're going to get different performance levels because there are features in there that have slightly different orders of magnitude than the others. Okay? So definitely take some time to go through this if you haven't. Go for it, solve it. Okay? You're going to, if you do it right, you'll find that with like, where are we at? This is decision trees. Decision trees, after you one-hot encode, you're going to get a test set accuracy like 98.2%, something close. You'll see on the confusion matrix, right, that there doesn't appear to be really much in the way of systematic error. It's just that chin straps, there's a couple of chin straps that get confused with the other penguins, right? Oh, and that's in comparison to before we used sex, right? Before we used sex, we had 95.5%, not 98% accuracy. So adding sex did help out. And it was some chin straps and some adeles that were getting confused before we made sex a categorical X variable. Okay? And when you go scroll down to nearest neighbors, you'll find out when you standardize, you'll get something like 99% accurate on the test set. But if you don't standardize the measurements, you'll get something like 81% or 82% accurate. Right? And you could even convince yourself that you don't have to standardize for decision trees if you take my code, modify it, and try a standardized version with decision trees. You should find something very close, if not exactly the same, to the non-standardized version that we set you out with. Okay? So do explore this. This is the first time you see a lot of the kinds of dark arts, I guess, of machine learning, right? It's not just about, oh, this is the algorithm. It's about how we deal with everything around it, setting up from the data that comes in into the features that we give it, right? Those are transformations. And we're going to take raw data and turn it into useful features. And the way we do that, well, it depends on the nature of the algorithm. We got to understand what the algorithm is giving us to work with to tell us how we want to transform that. So, any questions on this stuff? Did anybody solve the notebook completely? It wasn't like it was a hard thing. There's just a couple of lines in each one of these cells. Yeah? Got a few, yeah?
I have a question.
Yeah.
Is it always, like as a rule of thumb, is it always good to scale?
Yeah, I don't think, I can't think of something off the top of my head where it's gonna screw you over. So if you were just gonna, like, I just want a recipe to follow it, scaling is rarely the wrong choice. The only time I could think of when that might be the wrong choice is if those orders of magnitude difference between two features actually should translate into importance differences in your problem, right? Generically, I can't think of an example of that off the top of my head, but that would be the reason, right? Yeah, I mean, you could argue whether gene expression differences really would be like that or not, but most people would probably think so. Okay. So yeah, so there's the notebook. Please play with it if you haven't finished that. Okay. In the meantime, I just want to quickly finish up the nearest neighbor stuff. You probably saw in the pre-lectures a long time ago how nearest neighbors works. It's not hard. We calculate distances away from a given test point to the training set, right? And just generically, that means that at test time, stuff is slow. Whereas at training time, it's literally just write the training set into memory super fast, okay? Nearest neighbors have order constant time complexity at training, and order n, order the size of the data set, the training set, at test time. And that is basically the inverse of every other algorithm you will ever see. Most other algorithms take more time at training and less time at testing. Okay? We also talked about the fact that you should be aware of that more neighbors means more regularization. So what's happening is when you increase the number of neighbors who get to vote, what you're taking is a bigger sample, right? And, well, we all know statistics that when you have small sample size, you get wacky results, right? Random events at small sample size can dominate and give you bizarre answers. But when you have bigger sample sizes, then you're less likely, stuff on average is going to average out. That's the idea of averages and the law of large numbers, right? So we want large numbers for large samples when we can get them. It will tend to regularize things, whereas with one nearest neighbor, you're going to get the wacko stuff, right? There's a noisy sample over here in blue territory of the reds, and therefore it forms a red island in the middle of blue land. But when we go to higher number of neighbors, that one sample can't influence stuff because the sample radius is bigger. Okay? So one other thing, the reason why I really went through these slides instead of just assuming that you saw the pre-lecture, is that nearest neighbors is an algorithm that suffers greatly from the curse of dimensionality. And I guess if I was more dramatic, I would say something like dun, 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 right? So the curse of dimensionality is generically true in a lot of statistics. It's about sample density. I have 1,000 data points, okay? And when I have 1,000 data points and I'm trying to get an accurate picture of a single variable, let me just make some dumb assumptions that we typically make in statistics. I'm going to assume that my 1,000 data points are randomly distributed across the entire interval of the x-axis, okay? Well, with 1,000 data points, I'm going to have a pretty good picture of the x-axis, right? I'm going to have a good picture of the shape. So the standard thing is that if we want to know, right, over half the interval of the x-axis, what percent of the data is in that, right? It's 42% in this random sample that I've got. Because one variable, right, 1,000 data points, most of them, like roughly half of them are going to fall inside the half interval. Well, when I go up to 2D, that means my half interval is half of the x1 and half of the x2. So already you're thinking, oh my God, that's only a quarter of the area. But the sample density is worse than a quarter. The sample density is only 14%. And it goes worse than that when we go up to the cube, where we know that we're going to be seeing 1/8 of the volume of the cube on the half interval. We're down to much less than 1/8, 7% of the data captured. Okay? In general, this scales up with 1/d. If we need a certain density of stuff, we need to increase our sample size with the power of the number of dimensions. So that sucks rocks, right? This, to be clear, the 1/d is the density sampling, right? So that's why it goes down ridiculously with the number of dimensions. Okay. So think about this for nearest neighbors. To get a good data sample in your 7-sample neighborhood or your 13-sample neighborhood, no even numbers, right? Well, you need to have lots of good sampling in that region, or else you're not going to get an accurate picture. If your sampling is super sparse in 100 dimensions, that 13th nearest neighbor might be very, very far away in the vector space. Still your 13th nearest neighbor, but the distance to that one is very far. It's not really a comparable sample. So nearest neighbors, like when you get large numbers of variables, the number of samples must be very, very big, or else you are not going to get an accurate picture. You'll get predictions, they'll just be shit predictions, right? Because the algorithm's always going to give you an answer. It's just whether it's any good. So generically speaking, nearest neighbors approaches are not good unless you have orders of magnitude more samples than you have variables. Multiple orders of magnitude bigger. And generically, that's even true for anything. Like you'd really, really hope to have at least 100-fold more samples than variables on almost anything you could think of. But in nearest neighbors land, you want lots more even than that. Okay. And this is a visualization that may or may not help you, right? If you took this 2-dimensional sampling density here, and you just collapsed it down to 1 dimension, so like this red dot is this one here, and this red dot is that one, and whatever, I can't really see. This red dot, I guess, is that one over there, right? You could see like, 5 nearest neighbors or 3 nearest neighbors in 1D would be just fine in terms of accuracy, but in 3 nearest neighbors in the 2D is looking real sparse, right? Okay, cool, only 20 minutes late. But anybody got any questions on that stuff before I run away from nearest neighbors and trees? Okay. I know this one's a little bit of a whiplash lecture because I'm going through like one topic and then another topic and then a third topic. So do stop me. Although I do want to make time not to fall further behind, it is a little useless if I'm just sitting here talking to a bunch of people going, eh? Okay, brand new topic. What we're actually supposed to cover on Friday, but now we're a day late plus a smidgen. Logistic regression is a brand new kind of categorization technique. It is for categorization for discrete categories as the output, right? Like k-nearest neighbors and decision trees, right? We're all classifiers here. But it's so different because this is, once again, a bit of linear algebra. So k-nearest neighbors and decision trees, they don't have any linear algebra in them. Decision trees, they're just an algorithm. K-nearest neighbors, they're a distance. Neither one of them assumes anything like a Gaussian nature to any variables. They don't assume a linear decision boundary. They can fit any kind of wacky decision boundary you want. But logistic regression, because it's a linear algebra, it's got to be linear in the weights. And that means it makes a decision boundary that it is a line, right? So we're going to draw a line. Now, the big thing about this is that there's an inherent idea here, which is that if you have a data point which is far, far away from the decision boundary, you probably have greater confidence in what class that decision point is than if you had a data point that was lying right next to the decision boundary. Right next to the decision boundary, you know, noise. You might have a weird sample that crosses the border, okay? You could be wrong right close to the boundary. But far away from the boundary, you're going to be very sure this is positive class. And if you're far away from the boundary over here, you're going to be really sure that's negative. So that is the intuition that makes logistic regression, because what logistic regression does is it turns that distance into a probability of classification. So the further away you are, the more sure you are about which class you're in. Now we're going to write this, right? There's two steps to this. Number one, estimate a probability. This is the probability that a sample is positive class given the input and the weights that we're working with. Okay, that's a probability estimate. But we're also in this algorithm, we just flat say, okay, given that probability, I have to binarize the situation. I have to say, are you positive or are you negative? And I'm going to make my decision at the 50-50 line right here, right? Anything that's just over the edge, I am going to call positive class. Anything that's just over the edge this way, I'm going to call negative class, even though I'm not very confident in that judgment. So two components, the probability and the actual decision. Okay, this faces us with a problem, because distances off the decision boundary can go anywhere from 0 to infinity. So we need to squish 0 to infinity into a probability, which means we have to squish it into a number between 0 and 1, because that's where probabilities lie. Our friend in doing this is the so-called logistic function. It's this S-shaped curve. So you can go off here, you can go towards infinity, positive infinity, or you can go towards a negative infinity. And this will always asymptotically approach, but never quite reach 1 or 0. So it's the perfect function for squishing numbers between minus infinity and plus infinity into numbers between 0 and 1. Okay. Just to note, I went over it in the pre-lecture, but there are two forms. These are exactly equivalent. I don't have the time to show you how that works. So let's look at the simplest case. We've got a 1D, single x variable situation. And at some point on the left side of this x variable, everything's negative class, and at some point on the right side, everything's positive class. We want our probability estimates to go from 0 to 1. Okay, so we put that sigmoid or logistic or logit, all words that mean the same thing, into there. And we're going to make our decision such that wherever we just go over the probability being equal at 0.50000001, that's got to be a positive class instance. And at 0.4999999, it's got to be a negative class instance. So just above and just below that halfway mark. If you do the math, so just a reminder, what the logistic function is it's the 1 over 1 plus e to the something. Okay? Well, to make this a linear algebra thing, all we got to do is put to the something be wx plus b. Right? Just like our ordinary least squares or any other linear thing, we've got the wx plus b form. It just goes in the something, e to the something bit. When you do that, you'll find that the location of that half is just minus b over w. And if you follow me on the pre-lecture, you'll see that I show you how that works, but it should be pretty obvious. Now, the thing is that there's an inverse of this, right? So the probability of being positive class does this. The probability of being negative class is literally 1 minus the probability of positive class, right? It's the inverse. So you can convince yourself with a little bit of algebra that this blue probability of the negative class curve is just take that negative sign right there and get rid of it. Okay? A little bit of algebra or looking at the pre-lectures will show you how that works. So we have two functions, positive class probability sigmoid, negative class probability sigmoid. They are just a sign flip away from each other. We can generalize this beyond one dimension. Okay? So it's instead of wx being single variables, these are now vectors. Exactly the same other than that, right? Now we just have a sigmoid function that operates not in one dimension, but in multiple dimensions, where this thing in here is w transpose x, or w dot x, however you want to operate on it. Okay? But it's just the same logistic function, just operating with vectors instead of single variables. And we have our negative version of the same thing, which is just a sign flip away, say probability of negative class. Okay. Quiz time. A, B, C, or D. What is the decision boundary? The decision boundary, the thing that separates positive class and negative class. Anybody want to yell it out? Give a reason why? What shape is it? Yeah? Is it C? Because this is the logistic function right here, right?
Yeah.
Okay.
Because the exponent, the E is the denominator.
Okay. Anybody want to argue? Yeah.
I would say A.
And why is that?
I think you said something earlier about decision boundaries being linear.
And that's why the pop quiz, because it's super easy to confuse these two, right? So yes, the answer is A. The decision boundary is a line. This is the probability, right? And remember, when do we make the decision? We make the decision right here, where the probability goes over 1/2. Okay? So maybe let's do another graphical interpretation to help you with it. This is my multiple dimension sigmoid. It's that logistic function generalized into higher dimensionality. So as I change my x values, right, these things, I'm going to go from very low probability of positive class over here to a very high probability. This guy's definitely positive class. This one's definitely negative class, right, for two x variables. And so, all right, where's my decision boundary? My decision boundary is where things go over 1/2. Now, generally speaking, that decision boundary is defined by that linear algebra in there, wx plus b, right? So in 2 dimensions is what we're showing here, but generically in any number of dimensions you care to, because it's linear algebra, that defines a hyperplane, right? This purple thing in here, this is wx plus b. That's the chopper. So the decision boundary is the intersection, which is always a line, even in super high dimensional spaces. Right? Wx plus b is a hyperplane, so it's much higher dimensionality than a line. But the point where the intersection lies is a line. Okay, so let's talk about training this baby. So we've got this magic formulation. This magic formulation combines the positive class view and the negative class view. Because remember, positive class is just an inverse of the negative class. And when we go to the logistic equation, that's just putting a sign flip in there. So, if I take the positive class version, e to the minus, and the negative class is just e without that minus, I can combine those two together by putting negative, the true value in here, as long as I do my labeling like this, right? If my positive class and negative class, for mathematical convenience, are notated as -1 and 1, then putting a -1 in here, putting a negative on top of it, and the result is going to be a positive out front, right? And if I put a minus a positive 1 out front, that yields a negative sign. Okay? So this minus the true value label, when my true value labels can only be -1 and +1, this is just a mathematical trick to combine both of these equations into one equation. This does not work if, for instance, you label negative class as a 0. Okay? So as long as we pick the tricky labels, we're good. Okay, does everybody follow that? Yeah, so we can't use 0, 1 for logistic regression. It has to be -1 and +1. Oh, the probability you get. Yeah, oh no, the probabilities cannot actually reach 0 and 1 because they are asymptotic. You're correct. They get real close, but they do not reach it. Okay, here is what we're trying to train, right? So here's our assumption. We assume that every single data point gets classified. And we're going to assume if our classifier makes a mistake, its mistakes on data point 36 are not correlated with its mistakes on data point 12. Okay? Each data point we're classifying, we have got some probability of screwing it up. And because the probabilities of screwing it up are completely independent, that means that the probabilities are multiplicative. The same way that rolling 2 dice snake eyes is 1/6 times 1/6. Probabilities multiply when they're independent. So our job is this. We want to maximize the probability of being correct. Remember, this is the probability of getting the right classification now, no matter whether it's positive class or negative class, because this little trick means we don't care whether a data point is positive class or negative class anymore. It's described by the same equation. So we're maximizing the probabilities being the correct probabilities here, regardless of it being positive or negative class. There's a little bit of a blank look going on in the room right now. So I'm going to pause for a second and see if anybody can ask a clarifying question. Yeah?
So for that, we want to maximize the probabilities that the probability is correct.
Yes. So remember that this is now like what this means is this stuff in here, ignore the rest of it. this is going to be a number close to 1 when we want it to be a number close to 1 when it's a positive class instance. And we want it to be a number close to 0 when it's a negative class instance. And remember that, so when we have the negative class thing, it's going to be close to 1 for negative class. This is good over there. And this is good over there, right? These numbers are both going to be close to 1 over here when it's describing the negative class or the positive class properly. Yeah?
Is that why we label y with negative 1 and 1?
Sorry, I couldn't hear you.
I mean, is that why we use y to be negative 1 and 1? It's one to maximize the probability.
Exactly. We've now flipped the negative class equation from being close to 0 to being close to 1 when we are actually looking at a negative instance, right? So just look at the fact that those probabilities are inverse. Know that the minus y trick means that if we're looking at a real negative class instance, saying it's negative class gives us an output of close to 1, right? When we're looking at a real positive class instance, saying that it is positive class gives us an output close to 1. We want to, therefore, always have the logistic equation here be close to 1 for every single data point. We want to maximize that product of correct probability labeling. Okay? I know it's a little confusing because we have made a couple of switches of viewpoint here, but we want to maximize every data point being correctly labeled is how you should read that. Okay, so let's bring it home. So this is our product of probabilities. We hate products. They're annoying. They're not computationally efficient. So let's do some monotonic transformations to remove products and turn it into a sum. We know that if we take the natural log of a product, we can pull that product outside the natural log and turn it into a sum of the logs. We have simultaneously made another switch, which is to turn it from a maximization problem into a minimization problem just because we're used to thinking that way. It doesn't matter. They're equivalent. But in machine learning land, everybody thinks in terms of minimization instead of maximization. So by turning the max into a min, I generated a negative 1, and I just pulled that negative 1 over to here. Okay. One final transformation. Take that negative sign, move it inside the natural log. That means it went from being a multiply by minus 1 to a power minus 1. Power minus 1 means we get to move this denominator up here and get rid of the numerator, right? Okay, this is it. This is the form. This is the loss function. This is called the log loss. For obvious reasons, there's a log, yo. All right. So, if we're going to do an example of this, we've got a data set here. It's got one single x value, and every x value has an associated correct label. This is a negative class instance. This is a positive class instance. This one's negative class, right? So how would we do that? Well, so wx plus b. So the log loss is going to be minus 1.1 times w plus b. Put it in there. Put in 3.2, right, times w plus b. Right? For the positive class and negative class instances, right, this minus 1 lives out here, and it kills the negative sign, because that was the negative class instance. This one's a positive class instance, so the negative sign is there. You can literally add that up, and you can literally solve for W. Okay, so we want to find the best parameters W and B that maximize the probabilities, which is equivalent to minimizing the log loss. I'm pretty sure you're going to have to review this, so I'm going to skip on in the interest of time. So, all right, one thing you may or may not realize already is that this is not a solution we can just find analytically. We're going to have to gradient descent this loss function. So well, that means we need a derivative. So we're left with the question of what is the derivative of our loss function? So I did this in the pre-lecture. I'm going to bomb it real fast right now, okay? So the derivative with respect to W, we're going to have to do two things right now. We're going to have to chain rule to get to the derivative of the stuff inside the ln, okay? So stuff inside the natural log, its derivative is the derivative of natural log is 1 over the stuff. That's the definition of a natural log, actually, if you remember that from calc. And then we got to chain rule the stuff inside, right? So this is the derivative of the natural log is 1 over x. There's the natural log derivative. And then we got to chain rule with the stuff inside, right? The stuff inside, well, there's an exponential right here. So derivative of an exponential is an exponential. So same deal. And then we got a chain rule for the stuff inside the exponential. The stuff inside the exponential is a linear function, wx plus b. Its derivative is, with respect to w, is minus y xi. The minus y term, the xi term, the w goes away, right? So there's another little step in here where we do +1 -1 to enable us to factor it out. This is a bit of algebra. I hate this. It's not the kind of thing I would ever think of to do, but somebody thought of doing it. And in the end, you can simplify this down. And the beauty here is that what you've simplified it down to is 1 minus the logistic function. That's what that is. It's a logistic function again. Times minus y xi. Right? It is literally the derivative of the logistic function is 1 minus the logistic function times minus y x of I. Pretty awesome. So that is it. When you look at the derivative of the bias term, all that happens is that the x part goes away, right? There's no x for the bias term because the bias term is independent of the x. So this is generically the shape of the log loss, where this axis is yi wx plus b. It's the stuff inside the logistic function, right? The linear algebra. In other words, let's think about what that means. What is yi wx plus b? This is the distance away from the decision boundary. When you are far away from the decision boundary, in the proper direction, that's what the yi part does, right? When you're on the right side of the decision boundary and you're far away from the decision boundary, your loss approaches 0 asymptotically. What happens if yi is the wrong sign? Well, you're over here. If you're anywhere over the decision boundary, you've got some decent error in the fact that that data point is on the wrong side of the decision boundary. If you're very far away from the decision boundary and on the wrong side, you're going asymptotically huge. The loss is big for any data point that's not just on the wrong side of the line, it's far on the wrong side of the line. okay? So think about what this means. This means that anything that's just on the correct side of the line has got a little bit of loss, but not a lot. And if you're well on the right side, you've got basically no error. This is a recipe for finding a decision boundary that tries to make sure that points are well classified with high probability, and that means that we try to keep them relatively far from the decision boundary itself. So if we had a bunch of data points that were very well separated, we will not draw the decision boundary like this, which would be bad, because all the red points are pretty close to the decision boundary. We're going to draw the decision boundary like that, where it's very well spaced. All right? So, we're going to gradient descent this. We already showed you how to get to the derivatives of the log loss. It's a pretty simple derivative. As always, what does gradient descent mean? It means we start with some weight values. You can pick weight values randomly. You can start them at some particular location in the weight space. It doesn't matter. Wherever we're starting, what we're going to do is we're going to calculate that gradient. We're going to calculate the derivative of the loss function right there at that point in the weight space. That derivative always points to higher loss by convention. So we're going to flip it around, and we're going to have a negative step in the direction opposite the gradient, right? And we're not going to take a step that's a number smaller than 1, a number between 0 and 1. We're going to take a step lambda in the direction of the gradient and roll down the hill. Okay, anybody got gradient descent questions? Questions about all these derivatives? People are just like knowing that they're just going to have to review this stuff more than once before it really sinks in. Okay, I'll let you do that. In the meantime, an important thing to note is that what we're doing is we are approximating the hard loss. The hard loss is a 0, 1, where 0 loss happens when we're right, 1 loss happens when we've misclassified. It's a misclassification error loss, right? That is inherently what we want to get rid of. We want to get rid of misclassifications. It's the most natural thing in the world to think of doing a classifier as minimizing misclassifications. The problem is this: you cannot gradient descent that. Why? Because the 0, 1 loss is 1 where we've fucked up, and it's 0 everywhere else. That's discontinuous. There's no derivative here, right? Derivative does not exist. Oh, guess what the derivative is over here? It's 0, right? So everywhere we know what the derivative is, it's 0, so we can't descend because there's no direction. And everywhere we actually care about, the derivative doesn't exist. So we can't do that. Instead, the log loss looks like this. And if you draw the log loss on top of the 0, 1 loss, you can see it's kind of sort of a bad approximation, right? At least in the narrow confines near the decision boundary, right? It's kind of the same-ish. Obviously, it becomes very big over here, right? But nearby the 0 point, nearby the 0 error point, it is close enough. And importantly, because of its shape, it has a gradient at every point. So we can gradient descent it. Okay. So yeah, This thing is well normalized. It explicitly estimates probabilities. It's easy computationally because it's a bunch of sums. Bad thing is it's only indirectly minimizing the actual misclassification error. And it is super dependent on good features, right? If you don't standardize things, then you have the order of magnitude problem between features. This thing's going to break. And it's no good for feature selection because every variable is just as important as every other variable, right? Okay, that's it. We did it. Whew. Somehow we made it. Thank you very much. Good luck on revising. Feel free to ask questions, discussion sections here. May the force be with you. Hey.
So my A2 was working fine and I was about to submit it. Friday evening